Welcome to the lecture series for CTI 120 at Cape Fear Community College. My name is John Armke, and I will be your instructor for this semester. Chapter 1 is about Introduction to Networking, so there's going to be a couple of broad topics that we will deal with in order to give you a grounding in what to expect for the coming semester's lecture series. So we have 6 objectives today. We're going to distinguish between client-server and peer-to-peer models for network control and network access types. We're going to identify different types of applications and protocols that are used on a network. We're going to look at some hardware devices as well as the most common physical topologies. We're going to look at the 7 layers of the OSI model, which is the most common organizational model used to describe the flow of network traffic from a requesting client to a delivering server and back again. We're also going to look at best practices for safety when working with computers. And then lastly, we'll look at the 7-step troubleshooting model for solving a networking problem. Some of you may previously have learned a 6-step troubleshooting model, but this is the same thing with some minor modifications, which we'll see when we get there. As we begin, let's look at some terminology. Topology is a word that we hear quite a bit in networking because it describes how parts of a whole work together. A map, an arrangement, a layout. These are all things analogous to a topology. We have 2 primary methods of describing a topology. The topology we can see, the physical topology, and the topology that deals with the internal arrangement of control with a network. So a physical topology is the cables, the infrastructure devices, and the end devices, and how they all fit together to create the networks that we use. The logical topology deals with how these things are controlled, how access is managed. So different users and programs will gain access to the network via this logical topology. It may be that you have a switch that is your control for local traffic. You may be accessing a remote network which requires the use of a router. All of these things are facilitated by that logical topology. A goes to B goes to C. In order to control all these things at a software level, we have to involve what's called a network operating system. Now, this is a specific operating system that handles network proceedings. One could argue that the Windows operating systems going from NT forward predominantly included Windows, even as far back as Windows 3.1.1 with workgroups. In modern context, though, we think about it specifically as operating systems that focus on network enhanced operations. So things like Windows Server. Any server-based operating system would be considered a NOS. This is required by a client-server model because of how client-server works. Now, before we get into client-server, we're going to talk about one that's a little bit easier to set up, traditionally what we refer to as an ad hoc network in certain instances, to where we don't need a centralized device. Peer-to-peer, P2P as the abbreviation goes. The operating system of each computer on this network is responsible for controlling access to resources. So it's a bit more of a Wild West configuration. Every computer on a network has the ability to control its own connections. This means that computers, also called nodes or hosts, will form a logical group that has a hierarchy of 1. There is no overarching authority. You can share resources, you can deny access to resources. It's all local decision making. So each user can control what's present or not. Now, in order to connect in this way, every computer has its own local Windows account or equivalent connectivity through Mac or through Linux or whatever you're using. But that account only works on that computer. You're not able to go over to someone else's computer in the same peer-to-peer network, log in with those credentials, and be able to gain access to resources in the same way. Instead, we are able to manage connections going between those computers individually. So here we have a peer-to-peer network with a Mac OS desktop, an Ubuntu desktop, a Windows 10 desktop, a network printer, and the Mac OS device has a scanner connected. Now, as it stands, the Mac OS device could choose to share or not share that scanner at its discretion. But no one of these devices has any authority to control the others, except for, as I said, the scanner being slaved to the Mac OS because that's the primary network connection. That is a gateway control at that point. And they do communicate directly, meaning that the Mac OS device can speak to the Windows 10 device without having to have an interceding PC, if you will, sometimes a standalone device operating as a domain controller. Now, it may have a router, switch, or hub in between, but that's just going to facilitate the flow of traffic. There's no access control done there other than the physical. So there are some pros and cons. The advantageous side states that it is a simple configuration, as you can see from the figure that we showed in the previous slide. It's also a lot less expensive compared to other network models because we don't have the same level of infrastructure involved. We're not using a multi-layer switch or anything like that to facilitate smart switching or routing of traffic. We're not using a dedicated standalone firewall. We're not using a centralized domain controller. So we don't have that extra investment in terms of power, cabling, or hardware and software. Disadvantages are they're not terribly scalable. To be scalable means to expand or contract relative to the needs of the network users. So if we needed to, for instance, add, we had 10 users, we need to add another 20, it would take a little bit more in terms of internal resources to have the ACLs to contain those extra 20 users. Whereas with a centralized system, you only add those controls to one place. It's not necessarily secure either, and this one kind of confounds people when they first hear it, but logically it makes a lot of sense. Whenever you have a permission set up between two computers, you have a originating point and a destination point for every transaction network-wise. And usually, you're very aware of whether or not one computer or other has any problems, such as malware, viruses, etc. When you start expanding to 10, 20, 30 computers, because the permissions are individually controlled, if a computer who already has permissions on another device becomes compromised, then that means it's much easier for it to spread from one to the other. And let's say maybe that the antivirus on any of the other partner computers in that particular peer-to-peer group does not have the most current definitions. Well, then they can become compromised very easily because all we're looking at for those connections is the ACL to say this computer has this permission, this computer has this permission. And as long as that malware or other potentially hazardous executable goes, if it has permissions that fall within that through inheritance or similar items, then it's able to continue just as it was without any raised eyebrows, electronically speaking. It's also not great for large installations. The distributability of a peer-to-peer network means that there's a lot of potential for stuff to get bogged down. There's a lot of potential for loss or corruption of data if we have conflicting reports of things being delivered or distributed over peer-to-peer. That's not to say that peer-to-peer doesn't have its benefits, as we just read, but for particular situations, there is an alternative. The client-server model. Resources are managed by the NOS, or Network Operating System, via a centralized database called the Domain Controller. There is a database within that called the Active Directory, or AD, that contains all of the user account information and security access controls for the whole group of computers. So that logical group now has a centralized point to say where all the rules are, rather than saying, well, I'm going to go ahead and give a list of rules to computer A, a list of rules to computer B. I'm going to possibly put them in groups, or just have a master list in the AD that says they have access to this, 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 and this. You can almost think of it as a grid of checks and balances to say, okay, I have these 10 resources, I have these 10 computers. Wherever there is an approved interaction, there will be a 1. If there's a non-approved interaction, there will be a 0. And then you just have 100 little dots on the grid that tell you whether or not you've got yes or no to interact. The user can sign on to a network from any computer on that network and gain access to the AD's resources. So let's say, again, we've got 10 computers. So somebody who's usually logged into computer 1 goes over to computer 5. They can log in. They get the same credentials. It may take a little bit longer because a profile has to be built in the local registry, but they can still access those resources once that's processed. This is managed by what we call ADS, the Active Directory Domain Services, and this interacts with group policy to give them the ability to access various things. A lot of times, computers that are built into a domain in this way use what's called an imaging software to be able to set up disk images for their particular sets of access. This isn't great to do across departments. You don't want to re-image a computer in the accounting department to deal with marketing or with design and graphics, things like that. They usually have to be hardware specific. When we hear the term client, what we want to think of is a computer speaking from one to another to make a request. Clients don't share resources directly in this configuration. They have to go through that centralized database to ensure that permissions are processed accurately. Client computers access resources by way of those controlling servers. So we have a request that goes from the origination point to the domain controller to the resource and back again. So we have kind of a three-person interaction going on here. Whereas with peer-to-peer, we're able to communicate directly. So you can see in certain instances, peer-to-peer would be helpful because it's ostensibly faster. In certain instances, we would want to have a more secure connection, which is better facilitated by client-server. So here we see a diagram of a couple of devices connected to a domain controller, and we can see this little cylinder on the right-hand side that says domain database parenthesis active directory. So that's just kind of a visual representation of the contents of that domain controller's internal hard drive, if you will. Now here we see that the domain controller is a slightly different shape than the other computers, and that's really to be indicative of the fact that most servers built for this tend to be a little bit more computationally intensive. They have a little bit more firepower as far as their hardware goes. Sometimes, anywhere from 4 to 6 times as much as a standard desktop. That's why they tend to cost a lot more as well. They have larger power supplies, they have multiple processors present, they may have a massive amount of RAM, be hooked up to several hard drives simultaneously, and that's why they need specific operating systems to perform at their best. So, as I said, the NAS is responsible for being able to run the machine specifically to handle a particular operation based on the network's needs or based on client needs. So it manages data and resources, it manages access for authorized users, what files they have the ability to gain access to, any subnets that may be set up for user access, how computers communicate with one another, defining what protocols are able to be used, and then supplies applications to clients as needed. So here we see in the graphic on the right a screenshot from the About screen on a copy of RHEL 8 or Red Hat Enterprise Linux. Sometimes you'll hear it just called Red Hat, sometimes you'll hear it abbreviated as RHEL, and then of course you have your version number to kind of describe between. Now what's probably going on here is that this is being run in a virtual machine container. As we can see, virtualization is listed as Oracle from a central server, meaning that it's not actually being physically hosted on the client's hardware. It's borrowing from the processor and graphic stuff that's being handled on the server itself. Now it may have local hardware on the thin client, but the actual processing that's going on is coming from that physical interaction on the virtual machine of the server. So you can see under processor it says that it's an i7, but it says X2 at the end, which means that this thing has 2 i7-4980 HQs. So servers that have a NAS installed require more memory, processing, and storage, as I said. They may also have special hardware that provides network management functions. There may be serial links or interfaces to connect directly to routers or other items. They may also be using a KVM. And they may also have multiple NICs in order to connect to a failover network or to internal local hardwired subnets. So relative to a peer-to-peer network, we have credentials that are kept in one place. And one of the biggest advantages of that is that if a credential has to be modified, we do not have to change it in more than one place. It saves us from having errors or redundancy checks that fail. Multiple shared resource access is then centrally controlled, so that if we have resources that are available for a number of different user classes or can be accessed simultaneously, we can control what's called the atomicity, or the order in which saves or modifications are applied. This is really big, of course, for databases. We can also centralize how we monitor problems. We can run diagnostics, and we can correct any errors found from those diagnostics. And it is much more scalable. So previously we talked about a 10 computer network, so let's apply that in peer-to-peer form. That means that on every computer in that group, you have 9 sets of permissions that you have to deal with. So you say that for every computer, we have to have a grid that says, computer 1 has the rules for 2 through 10, 2 has 1, and then 3 through 10. So it's, you've got 90 individual rule sets. Whereas here, you're able to say, okay, I've only got 10 computers, so I've got 10 sets of rules for those, and that you're able to distribute them a little bit more readily. So at that point, we can say that the communication between computers, random number, 3 and 7 are the same thing as communications between 7 and 3. So we're able to take that big grid of 90 different communication rules, if you will, and cut it at least in half. There may be situations where there is no connection between 2 computers. Maybe one is isolated in some capacity. So in that way, we're able to reduce that connection list even further. Now, network services, things that the network controller will provide, are the resources that a network makes available. So that can be just data, like a file share, things like that, or applications. There are applications that run, you can hear this in the cloud computing world now. They have what's called IaaS, which is infrastructure as a service, PaaS, which is platform as a service, and then SaaS, software as a service. So this would be something like Photoshop. Photoshop has a lot of materials that are available for subscriptions, and you can do kind of an a la carte thing. You can pick out various items and choose what you wish to, quote unquote, subscribe to. And as long as your subscription is valid, then you are able to access those items, and they are sent to you via a network connection. In client-server applications, the process is that a client computer requests a particular resource, and then the server processes that request, checks the ACLs, access control lists, sees whether or not this request is legitimate, whether it's something that is able to be authenticated and to be approved, and then processes the response, either an error message, a modified response, or it's going to send the item that was originally requested. How does it do that? Well, we have to establish common rules of communication, and that is what we call a protocol. So if you think about, Star Wars, C-3PO identifies as a protocol droid who is fluent in over 6 million forms of communication. And that is because he is built to make sure that when one alien race speaks to another, or a machine is speaking to a human being, he can understand R2. Luke can too, but that's because he works with droids that speak that particular, he speaks astromech, or is able to understand it. At that point, he's able to facilitate communication between different species, different groups, things like that, because that is what he's designed for. He's trying to find the way that those two protocols mesh or fit in the middle. Primary protocols that we talk about in client-server applications are TCP and IP, so transmission control and internet protocols. Traditionally, we refer to them as a suite called TCP/IP. We don't often talk about them separately because they are so, I hate to use the buzzword, synergistic. They work together incredibly well. The suite or group of protocols that we call TCP/IP is used by the vast majority of OSs for communication on a network, especially where internet connectivity is concerned. So here we have a client application, web browser, requesting a page. The connection funnels through the various pathways of the internet and returns to a file server at a particular address. This file server is a specialized one called a web server, which provides HTML pages and multimedia that are encoded in a particular way. So in this case, the request is for a page called index.html. That web server tied to that domain name will go ahead and verify that that web page is present, loads a copy of it into a series of what are called frames, and then sends it back across the internet to return to that web browser. So we have the request, we have the transition, we have the receipt, the request is processed and then responded to. Then it passes back through the internet to the browser in question. So some popular client-server applications that we see on a consistent basis would be things like web services, so being able to access a web page, e-commerce, things like that. Email, FTP, file transfer protocol for those uninitiated. Telnet, which is traditionally what we use as an unencrypted method for being able to access a router or switch remotely. Other remote applications, especially something like remote desktop, which uses the 3389 port, if I'm not much mistaken, and allows a person to control access to a machine via an internet connection so that you can have remote tech support or things of that nature. So here we see email being sent. We have a sender using SMTP to send mail. The mail server is going to receive that information and use SMTP to send it between itself and another mail server. Those two mail servers will talk and be able to translate that information. And then to receive the information, it uses either POP3 or IMAP4. POP basically says I'm going to move the message from the server to a desktop client or similar. IMAP is you're able to log into the server, manipulate your email, and leave it as is. So POP, I often tell people, is like going to the post office. That's what the PO stands for, Post Office Protocol. You go to your PO box, you open it up, you take your message out, and you take it with you, so it's no longer kept on the server. Here we can see a remote desktop. We've got a desktop within a desktop, if you will. You can see the host machine in the background, and then we can see the local computer there being able to access different items. So let's look at some hardware, such as the LAN. The LAN is usually contained in a fairly small space, geographically speaking. So an office or a single building, maybe a small collection of buildings. Usually if it's multiple buildings, it'll be multiple individual LANs that are then collected together into a larger LAN or even into a WAN. A switch is a device that receives data from a port and then redirects it to another single or multiple ports. The thing about a switch that makes it much more helpful than something that preceded it called a hub is that it keeps track of what the history is, as it were. Not of what the data is, but where it came from. So let's say that port 1 is attached to IP address locally 192.168.1. I missed the octet there. 192.168.1.1. Port 5 is connected to 192.168.1.12. Let's say that the person who set this up had no concept of how to organize a subnet. Those two things, the port on which it came in and the IP address to which it belongs, sometimes even the MAC address of the NIC that is connected to that, will be retrieved and retained in a table. That switch table will then be able to give you information to say, okay, I've got a packet for this IP address, where does it go? Or I've got a packet that goes to this MAC address, which is what local traffic usually does. And it will make transitions on local traffic much faster because the translation between the two is no longer having to be repeated. It's able to eliminate that duplicate process. A star topology is what we traditionally use for switches because we have all end devices on a particular network connecting to one central device. Star topologies are also used with routers in certain instances. It just depends on how many switches may be involved, whether or not they're considered to be backboned into what we call a bus topology. So the network interface card, or NIC, is what we use to attach devices to the network. That is actually the port that's involved. More often than not, your NIC is going to be an RJ45 cable, also called an Ethernet cable. Sometimes it'll be Cat 5, 6, 6E, 7. But that's the port that it connects to. NICs can also be wireless. They can connect via Wi-Fi or other similar network standards to be able to get onto a network without a physical cable. So here we see a LAN connected with 5 computers, 2 printers, and a scanner. One connected directly, one not. And it's using a star topology because everything is centralized back to that primary point of network contact. And again, the switch is going to facilitate quick communication between all of these devices because it has a recorded knowledge of which port belongs to which MAC address and which IP address. Here we see a realistic switch on the left, big rack of switches, and then on the right we see some consumer grade switches that would be much more common in the home or small office environment. The one in the top right looks very much like the Cisco Catalyst 2960s that we use all the time, so that will be something that you'll be seeing again this semester. Here we see a laptop providing an onboard network port to connect to a wired network. So there's that RJ45 I was telling you about. I'm sure that does also have a wireless NIC that it can use to contact via Wi-Fi. The Ethernet adapter below with the PCI Express X1 interface is a single gigabit contact card. So we can see here that we've got the NIC that has a single import plug, the single RJ45, and then connects to the motherboard directly. You may see others that are built on to what's called an onboard connection, soldered directly onto the motherboard, or in the case of servers, you may see one that has two or sometimes even four network ports on it that all connect to different internal connections in separate networks. LANs can have multiple switches. Usually the backboning process is where we have central lines that connect the different segments of a network. Let's say that we have a building with 4 rooms. We've got a data closet, and then we've got 3 little office rooms. And all of those office rooms have their own subnets. Each of those subnets connect back to the data closet. The data closet then connects back to what's called the MDF, or main distribution frame, that passes information from the LAN to the ISP at what's called the demarcation point, or DMARC. If we have 3 or more switches daisy-chained together in a single line, it uses the bus topology I referenced before. Now, because each of these switches is using a star topology, we have created a hybrid topology. So here we can see 3 switches, each using a star topology, but the switches are chained into a bus, so we create the star bus topology. A router is different than a switch in that it doesn't deal with internal traffic, it deals with traffic between networks. So it goes outside of our local area. Now, routers are responsible for maintaining what's called a routing table to determine the best path for traffic to move from one network to the next. Routers can be used in small home networks to connect the home LAN to the internet and create what's called a SOHO network, small office / home office. You may also see what's just called a home network, which is a little bit less sophisticated. Industrial routers often have several network ports, one for each network it connects to, so it's kind of similar to what I was talking about with the various NICs that you may see. You can see here that we've got a combo device in the bottom of this graphic as opposed to a switch and router. The combo device is more accurately called a multifunction device. I think that's a little bit better than combo. I think combo just makes me think of snacks that I would buy at the ballpark. So a multifunction device includes several aspects of the hardware we've already discussed. It contains a switch for local traffic, a router for external traffic, and in the case you can see the antenna here, a wireless access point to be able to transmit information not only through a physical cable, but through radio frequency as well. Here we have 3 LANs connected by a router. So we have what's called an extended star, or a hierarchy topology. So we have a star of stars. Networks A, B, and C are all star topologies connected to a single switch, and all 3 switches are connected to a single router. This leads to the hierarchy of networks that eventually becomes the internet. A metropolitan area is a group of connected LANs in the same geographical area, also known as a CAN. CANs, of course, are specifically limited to campuses for businesses or educational facilities. So, depending on how you argue it, Cape Fear's network, if you're talking about Surf City, Burgaw, downtown, and North Campus, could be considered a CAN because they are connected to one another. They do have the ability to transmit information so that we can access resources in the same capacity. You have a single sign-on that you use for all of your Cape Fear assignments and services that is attached to our CAN, if you will. A WAN, or wide area network, is a much larger geographical area. The internet itself qualifies as a WAN because it is the largest network on the globe, because it covers the entire globe. MANs and WANs often use different transmission methods than LANs. They use different types of signaling. They often use specific serial transmission types, DCE or DTE, more often than not if there's a serial connection. And it will also often use different media. So whereas we might have 10 base 100 connections to run 100 megabits for a very small end device, we'll probably need a gigabit connection for traditional high-end stuff, and then be able to connect to fiber connections as well. So if we use fiber links high-speed connections between WANs. That's going to be very different than what we use internally for a LAN. Personal area networks are the smallest. These are where you might be hotspotting your smartphone and your computer, one to the other, or if you're using a Bluetooth connection between yourself and a fitness device or a pair of headphones, that sort of thing. That is a local personal area network, usually what's called a piconet in certain instances, probably less than 100-foot radius between two devices. Beyond that, the range is not sustainable. So here we can see that we have two star bus topologies. We've got two LANs on one in San Francisco, one in Philadelphia. Each one has a sub LAN of a couple of computers each on a switch. But the WAN link is going between San Francisco and Philadelphia and is able to connect the two as if they were still physically present directly to one another. So how does all this information get processed? How do we send things from San Francisco to Philadelphia and maintain not only security, but internal consistency, making sure that files get put back together the same way that they were sent? So a browser and a web server, just for an example, communicate the same way that we would think of, in abstract terms, of information being sent like through a letterbox. You know, write a letter, stick it in the mail, and be able to send it. Very, very similar. So a browser is going to communicate with the operating system and hardware by assembling a message, correctly formatting it, and processing it through from a digital signal that's stored in the hard drive to an electronic signal that can be sent through the NIC, either as radio waves, light pulses, or electronic pulses. The cabling and other infrastructure that we use to support the network going from A to B across a WAN, if you will. And then the decoding process that occurs at the recipient's location, going from hardware to operating system to web server. So we have the ability to encode and decode, or encapsulate or de-encapsulate these messages. So in order to standardize these transmissions, we decided to start using a open standard reference model called the Open Systems Interconnection model. It's 7 layers deep and categorizes the layers of communication from the physical layer to what's called the data link layer, which is a transitory layer between 1 and 3, the network layer, transport layer, session, presentation, and application. Now in the TCP/IP model, which is closely related to the OSI model, we combine a couple of these different layers. Physical and data link are combined to talk about what's called network access. Session, presentation, and application are merged together in order to talk about the application layer. And that's because the functionality of those different groups tends to be very closely related when we're talking about TCP/IP. Obviously, OSI has to maintain a stronger level of stratification to make sure that we can compensate or accommodate, if you will, the different types of network transmissions that may go on. We may supersede Ethernet one day, and of course the OSI should then be rewritten to handle that. So here we can see the structure of the OSI relative to how hardware and software will communicate. So the 3 layers we talked about before were the applications, the OS, and the hardware. The applications would be things like your web browser, your email client, or an FTP client, stuff that the user faces. Then we get into the OS, and we have to deal with how these protocols talk. So TCP/IP has a couple of protocols that are embedded in the operating system to facilitate these different items. The World Wide Web browser, or your standard web browser, so Firefox, Chrome, Microsoft Edge, uses usually either HTTP or HTTPS, depending on whether or not you have a secure connection. Email uses SMTP to send, POP and IMAP to retrieve, FTP to upload files and download them, FTPS for security. There is also one called TFTP, which is Trivial File Transfer Protocol, which we'll talk about later on. Session, presentation, and application do all work together to facilitate this transition into the operating system from the applications. Deals with formatting, communication, and management of the communication session between host and client. Host and server, excuse me. When we move down into the network layer and transport layers, layers 3 and 4, we see that we have to start establishing a new set of protocols. TCP, in order to handle the transmission if we want to use what's called a connection-oriented protocol, or a UDP if we're not concerned about maintaining a consistent connection, we just want to transmit. Then at the network layer we have IP for Internet Protocol, unique addressing, ICMP for control messages, and ARP for dealing with layer 3 switches to be able to communicate effectively regarding what device belongs to which, being able to resolve addresses. That's what ARP stands for, is address resolution. We get down into layers 1 and 2. Layer 2, as I said a little bit earlier, is a transitory layer. It facilitates communication between layers 1 and 3 by having two parts. The MAC sublayer in layer 2 deals with media access control, the physical transition of data from a digital storage to an electronic, optical, or radio frequency based impulse. It also has a layer called the LLC, the logical link control sublayer, and that facilitates returning information from a physical medium to a digital one. So if we're passing upwards, we focus more on the transition into the LLC. If we focus passing it downwards to the physical layer, then obviously we worry about the MAC. So there we have our three categories. So we have a message that starts out very high concept, something like sending an email. We've got an email address to send and receive. We've got priorities. We've got a link. We've got text. We've got images, possibly signatures. All of that has to be encoded, and it has to be done sequentially, and it has to be done in the correct sequence. So we see that that's what the layers are good for. And when the item is received on the opposite side, we literally do the exact same process but in reverse to peel off the various formatting and encapsulation that's done in order to send a message in the first place. So the application layer describes the interface between an application here and an application on another computer. We've got, for example, a web application that's accessing a web page. We've got our web browser client on our end. We click on a link, and we need to retrieve the document that powers that page, the HTML, the CSS, whatever else is present. And that interface between client and server has to be facilitated, and that starts the application layer. So providing services to a user, providing services to a system, that has to be established. The payload or data that's passed between two applications or utilities has to be identified. So let's say that we're sending an attachment with our email. That has to be combined with the email text itself to create what's called the payload. So the payload is the whole message. It's not just, 1.2 or 126.jpg or whatever it is, whatever random file. It's going to be, here's the email message, here's the metadata, here's the picture, here's the header and trailer to identify where it's supposed to go. So there's a lot of material being attached. The presentation layer deals with formatting, compressing, or encrypting this message so that it can be processed by both host and by server. The session layer deals with synchronizing data between the applications and recovering information that may be lost if things don't arrive intact. And again, here it talks about how these layers are intertwined, and it's often difficult to distinguish between them as they're working. Now, most tasks are performed by the operating system when an application makes what's called an API call. API, or Application Programming Interface, is the method an application uses when it makes a request of the OS. APIs are often what programmers deal with in order to connect between different, what we call, agents. So if you work with media servers or things like that, you may connect to the TV DB or the movie DB to be able to do what's called a scrape. Let's say that you are uploading a song to your media server that you want to use for a party that you're having later on in the week, somebody's birthday party, and you want to make sure there's a good mix. Being able to identify that information from the MP3, you can go ahead and connect to Grace Node or whatever database you want. You'll be able to upload the information. It will analyze the songs and return what's called ID3 tag information about it. So the API is just a bunch of predefined methods for doing certain things. So if you ask an API to do X, Y, or Z task, that application can perform it both on the local and on the remote hosts. Transport layer is responsible for moving payloads from one application to another, and the two main ones, as we talked about, are TCP and UDP. Now, it's important to notice the distinction between the two. TCP must make a connection with the end host and verify the data that was transmitted. That is why it's called a connection-oriented protocol. UDP, User Datagram Protocol, does not facilitate this. If you want error checking or connection-based materials, either you need to use TCP or you have to involve a different protocol at an upper layer. So in the session presentation and application layers, which, as I said a little bit ago, you can actually have facilitated. This is called a connectionless protocol. So it connects faster, it has less overhead, meaning that the frames are smaller, but it also means that you lose some of the intrinsic security and reliability that you would get with TCP. Protocols add their own information in an area at the beginning of the payload called a header, or sometimes called a preamble. The preamble is actually what comes before a header in most cases, but sometimes they're interchangeable. The process of adding a header to data inherited from a previous layer is called encapsulation. So we get, these segments of a payload, and then we add information to it to be able to determine where it's supposed to go by layer. We'll talk about that as we go. We have a nice graphic for that. For instance, the transport layer header tells the application that a particular packet belongs to, or a particular frame belongs to, called a port number. So let's say that it's an HTTP packet. Then it's going to go under port 80 or port 8080 so that it identifies that it's supposed to go to the web browser. There are what are called well-known ports, registered ports, and dynamic ports. Well-known ports usually go from 0 to 1024 and are specifically assigned to internal services. So things like 110 would be something that would be used for, I believe that's for POP. 443 would be for IMAP. I think it's either 52 or 55 for SMTP. So there's a couple of different ports that are specifically assigned to protocols that are used all the time. If you go to what are called registered ports, those go from 1025 to, I want to say 65,536. Anything above that is considered a dynamic port that can be changed. I may have to double check that definition, but I think we talk about it in a later chapter. But the idea is that the port tells the receiving application, hey, this is where this belongs. So if you've got communications that are going on between apps like Battle.net or Discord or Adobe Air or some kind of cloud service like OneDrive, that stuff has to be identified so that it correctly processes. If a message is too large, the original payload has to be cut up into smaller messages called segments. Those segments can be further divided, if need be, into what are called fragments. Fragments are not desirable, but it sometimes has to be done depending on the limitations of the hardware that's passing information from one point to another. Instead of calling it a segment on the UDP side, they instead call it a datagram, which makes sense because the D in UDP stands for datagram. At the network layer, the network layer header is added, which gives you the IP address, both sending and receiving, that needs to be attached to the segment or datagram given. Now, the segment or datagram can often be more generically referred to as a PDU, Protocol Data Unit. So at the transport layer, we're talking about a segment or datagram. There's still two different names that can be applied based on what protocol is being used. When we add the network layer, we put that header on, it's now called a packet, and that's pretty much universal. The IP address is going to uniquely identify each host on their respective network. Now, if we're doing local traffic, we're talking about a network address that is part of a subnet. If we're talking about something that's passing between networks, that's when we have to assign it based on the incoming request or outgoing delivery. But it has to be unique. They cannot be the same address on the same network. Now, they can be translated. You get into what's called NAT, Network Address Translation, that allows you to have two subnets on a private subnet rather talk to one another. IP relies on several routing protocols to find the best route for a packet to move between one or two. So things like ICMP, ARP, what's called IGRIP, EIGRP, it's external, or I'm sorry, Enhanced Internal Gateway Routing Protocol. Something I will tell you, this is a little bit of inside baseball. You get used to using the items to describe your transitions from one place to another without remembering what they stand for. And it's important to know what they stand for because you get in there and you know the function is often described by the name. But when we use the acronym, it's difficult to make sure that we're paying attention to what that meaning is. As I said, fragmentation is possible if we have large packets that need to be broken apart, limiting, the hardware or something. Maybe we have a layer 3 switch that needs to make a packet smaller in order to facilitate its travel more easily. Layers 2 and 1 interface with the physical hardware. As I said, we have the different sub-layers that pass either up or down and facilitate standardization of information passing through. So the type of networking hardware or technology used on a network determine what type of link layer protocol is used. So the dynamic link layer controls at the LLC are going to be determined differently if there's one for Ethernet or one for Wi-Fi. The control information is put in a link layer header, and now the trailer will terminate the packet, and that is now called a frame. So just giving you a rundown, we go from the port number, which is given to the segment. We have the IP address, which is given to the packet, and then we have the MAC address information, which is given to the frame. So the frame is now the final piece of information that passes into the physical layer to be transmitted as bits. Now these bits can be transmitted either through radio frequency, light pulses, or electronic impulses. So the thing about MACs is that these are hardware addresses. They're embedded on every network adapter and are considered to be short range to find things locally. The good news is that that can also globally identify what type of interface is being used. So if you have a Dell network interface card, your MAC address will actually describe the first 24 bits is what's called the OUI, Organizationally Unique Identifier, which will say this was manufactured by Dell. And then you have what's called the interface ID, which is the last 24 bits. MACs are 48 bits long, and it tells you what interface it was put together. So kind of like when you have an area code and a phone number, there's 3 separate parts. The area code gives you a large space. The local exchange is the second 3 numbers, which gives you the area within that area code, and then the last 4 are usually unique to a physical location, the way phone numbers were originally assigned. So the last one we get to is the physical layer, and it's the simplest of the 7. And again, as I said, it can be passed through radio frequency, so wavelengths in the air, voltage on a copper wire, or light impulses via fiber optics. So here's our layout of the different PDUs, protocol data units, and we can see either just the standard model layer, the name that belongs to it, and then the extremely technical name if you want to get really hard up on it. So layer 7 PDU, which is preserved all the way through layer 5, 4, 3, 2, and 1. Here we can see the graphic representation of how a packet passes into a frame or into a segment, up or down, depending on whether or not it's being sent or received. So we see here the payload represented by the yellow P. Let me go and grab my laser pointer real quick. Okay, so follow the bouncing dot. We can see the payload here at P. We can also see the HP here for the first header with the packet, or payload rather, I'm sorry, I was CP and think packet. The header and the first piece of the payload, which becomes a segment, gives us that port number. The second header is added, gives us a packet. The third header and the trailer is added to give us the frame. When we get over to the switch, in order to pass things through local traffic, which is what the switch is responsible for, it needs the MAC address, and that's done at the data link layer, layer 2. So we take the bits, translate them into some digital information that can be read, and it's read by the switch to say, okay, this is the local address. Now it's going to go ahead and put that information back on and say, I'm going to send you off to the router to go to an external piece of the network. The router is going to receive that information. It's going to read the same data link information as the switch, but it's also going to go up one layer higher. So now I referred to this a little bit ago. There's also what's called a layer 3 switch, which does some of the same information as a router, facilitates traffic in a bit different capacity. Traditionally, switches only handle up to layer 2. But layer 3, now we see the network address layer to give us our IP address, if you will, and it says, okay, router to router, I need to find which network this goes to and be able to pass it through. And this may have to happen several times. And at each location, as this information gets peeled off, it has to be reapplied. So at layer 2 on the switch, it's going to go ahead and take off that header and trailer, read the information that's necessary, and pass it back through with a new header and trailer, which may sometimes duplicate the same information, other than the destination. The web server here on the very end, you can see that we're doing the exact same item that we had at the browser, except for instead of adding information, we are subtracting it. So the physical layer over on the web server receives the full frame, all three headers, the payload, and the trailer, and it starts peeling off the different pieces. So it says, okay, we're going to take off that header and trailer. We're now at a packet. Packet's going to read its information, peel off that header, pass it upwards. It's now a segment. We've got our port number. We're going to peel off that header and pass the payload up. Now, as the payload passes through layers 5, 6, and 7, those data segments, or payload segments rather, will be reattached to one another in the correct order if it's TCP, or in whatever order they were received if it's UDP, in order to provide information to the requesting application. Turn off the pointer. Now, the next to last section we're going to talk about is safety procedures. We need to know how to protect ourselves, we need to know how to protect our equipment, and we know how to protect each other. So let's look at some practices here. Always know your best escape route, where your emergency exit is. Fire suppression systems and data centers include things like an alert system, so you may have an audible alert, portable fire extinguishers, emergency cutoff switches, and suppression agents. Be aware of what's being used in your particular building, because you don't necessarily want to get caught in a room where halon's being deployed, or try and use a Class A extinguisher on a Class B fire. If you take my CTS 120 course, we talk about the differences between classes A, B, C, D, and K fires. Fail open or fail close. This is where a security system will either allow or deny access during a particular point of failure. In cases of things like a fire, you would probably want to have the system fail open, in that the doors would open outwards. But once things pass through, unless a particular signal has been given by the fire department or other emergency services, you would probably want certain doors, especially ones near sensitive information, to be closed, remain closed. The Material Safety Data Sheet, or MSDS, often explains how to properly handle substances, particular interactions that you would want to avoid, so things like physical shock or electrical shock. Physical shock being like you banging it into a harder object that could possibly cause it to be jolted. Heating, volatile vapors, health hazards, things like that. So, toxicity, how to ship it, how to get rid of it, what happens with a spill. Electrical and tool safety is generally regulated by an organization called OSHA, the Occupational Safety and Health Administration. This is a federal organization that is put together to ensure worker safety rights across the country. I'm sure some of you have gone to a job and been able to see on the wall this giant poster that says, you have rights, da 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 da, and it outlines all of these various things. Some of them may provide enlightening information in certain cases, because it's not always something that a job makes apparent. And this is not out of malice, it's just that the regulations in question are very long and very complex. OSHA regulations for power tools would be things like, make sure you're wearing the correct personal protective equipment, or PPE. Make sure you know how to maintain that equipment. Make sure you know how to identify when that particular equipment is failing or is compromised and needs to be replaced. Keep all tools in good condition. Make sure you properly store tools that are not in use and in their appropriate places. Use the right tool for the right job. You don't necessarily want to use a jackhammer on a tile floor on a second story, because you may punch straight through the floor. You'll want to get in there with a chisel and be able to knock up tiles and pry them up more gently, if you will. There are instances where, of course, you do need to use very aggressive methods, but we want to escalate correctly and make sure that we are applying things commensurate to the task. Let's make sure we watch out for trip hazards. We don't want to possibly put ourselves into a dangerous situation where you're going face first into the floor while you're carrying a box of light bulbs or similar. When lifting heavy objects, make sure that you follow the same guidelines that you would for any other heavy object lift. You want to treat your work and home environments the same. Your back is not meant to hoist things off the ground. You're not supposed to apply fulcrum pressure to it. You're supposed to use it as a straight support to keep your body aligned. Make sure your muscles are balanced. So make sure that the load is faced to where, when your arms are out, that you're holding it towards yourself and keeping that load towards a center point. You don't want it tipping away from you. Stand close to the object with your feet apart, keep your back straight, bend at the knees, and grip firmly. usually using gloves. For certain heavy objects, you may actually wish to slide a grip enhancement strap underneath. You'll sometimes see carrying straps or loading straps. What it does is it moves the lifting away from your hands towards the base of your forearm near where your elbow is. They're very inexpensive. I could definitely recommend them. I've used them several times. It's great for things like appliances that may have sharp metal edges. Gloves are also highly recommended. Make sure that you're lifting with your legs, arms, and shoulders, but not your back or stomach. Your back and stomach, in addition to providing a strong core, making sure that you do have the ability to lift things and pivot, is not meant for the entirety of these loads. The lifting should come from long bones, not from things that could easily tear, deform, or cause herniation. Keep the load close to your body and make sure that while you're holding it, you're not trying to rotate at the hips. You should probably turn by slowly kind of shuffling your feet left to right in kind of in a circle pattern. When you're putting the object down, very much like in the OSI, you want to make sure that you follow the same process, just in reverse. So you're going to keep your back as straight as you can and lower it while bending your knees. Static electricity, very dangerous component to deal with in the lab. We want to make sure that we keep the electrical balance between ourselves and our components as level as possible. How do we do that? By what's called grounding. Electrical components can be damaged by having a differential of electrical potential between two bodies. So your body and a RAM stick, your body and a hard drive, your body and another person. There can be a difference in the amount of electricity that each of you contains based on composition. A RAM stick is probably made out of something that's much more conductive than the human body. The human body actually has a lot of resistance depending on where you're testing. Static electricity can cause two different types of damage. Catastrophic failure, which is where the component is not able to be salvaged, and upset failures, which will merely cause the component to have to be reset. It may shorten its life, but it can limp along until it can be replaced. Before touching a component or another person in an electrically sensitive environment, make sure you ground yourself by wearing a strap. The ESD strap will essentially be connected to a live metal surface, which can then discharge electricity much more evenly and can keep it from building up in a place where you may touch a component and cause an accidental discharge. If you do not have a strap, you can touch the case before touching any component in order to disperse any built-up electrical potential, and making sure that the components that you do have are, where possible, stored in an anti-static bag. Whenever working with components, it's also important to understand that shutting down a computer, unplugging it, and discharging it are necessary to ensure that any built-up charge in the power supply has been dissipated. So here we see a person touching the chassis as well as being clipped in. The computer is unplugged and devices are correctly mounted so that they are not hanging off or possibly going to contact one another during the discharge process, and that cable management has been employed. Last that we're going to talk about today is dealing with troubleshooting. Troubleshooting is important, and it's making sure that it's methodical so that we don't accidentally skip steps. Step one is to identify a problem. That means user interviews, gathering information, observing and identifying symptoms, and determining what has changed from the point of function to non-function. Step two is to establish a theory of probable cause. Remember that we always wish to question the obvious. Just because it may seem obvious to us does not mean that it may not be obvious to someone else. It also may mean that somebody who didn't necessarily work with this device in a capacity of a professional could have made an easy mistake. It's important not to allow our burden of knowledge to make us blind to potential causes of damage. Test theories to determine cause. So we've established a theory, now it's time to test it. If the theory is confirmed, then we move on. If not, we loop back and move forward. If we have to, we can escalate. I tend to prefer to do that until after we've tested a couple of action plans first. But obviously, of course, don't waste your client's time by trying to continually bash your head against a wall, as it were. So either we've got our theory, we've got our action plan, we put it into place. If our theories do not yield positive fruit, if you will, we will then need to escalate it to someone whose potential to solve it may be greater than our own. At number 6, we want to verify functionality, and this is twofold. We want to make sure that we fully boot the system. We go from a cold boot, meaning that it's fully shut down, not just restarted. And then we go ahead and apply preventative measures where possible. Whenever you can, you want to make sure that you educate your clients so that way you don't have to get called out for the same simple items again and again and again. Whether or not they listen to you is immaterial, but ethically, it is best to provide that information. Last, we want to document our findings, actions, and outcomes. Now, this is something that should be done as you're going through, but I think the reason that they put it as a separate step is so that you can provide a summary for your client to be able to provide a rundown of what actually happened at the end. You may not necessarily want to sit down and be like, well, we tried this, 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 and this, and give them all of the things that didn't work, but you do want to give them the idea of what did work, so that way you have a clear idea of, this is why I came, this is what I did, this was the result. And then again, if you can include those preventative measures, that tends to be very beneficial. That is chapter 1. Obviously, you can go over the summary if you wish, but I want to make sure that you guys have these videos to be able to review in lieu of having in-class lectures. If you have any concerns or comments, please feel free to leave them below, or to email me directly, jearmke063@cfcc.edu. Anything else, please let me know as soon as possible. I always encourage feedback and comments. So if there's anything else you need, contact me through the approved methods. Other than that, have a wonderful week.